It's on? Okay. So, bonjour, hello, I am François Rideau from LegiLogic, and I'm going to tell you about verifying dApp computations on the blockchain. Is this working?
Yeah.
Yes. Okay. So, why blockchains? But first, take home points. I'm going to make blockchain distributed applications secure, scalable, and private, and by offering a suitably high-level programming model. A blockchain, the correct way to see them, in my opinion, is as a verifiable trace of computation. These are distributed computation, and you have a one verifiable trace that everyone agrees on. And you can then use game semantics to prove arbitrary invariance about this computation. We at LegiLogic are building a blockchain layer 2 operating system, a platform on which to develop distributed applications. And we're looking not just for employees, but also for academics to come join our research consortium, which is called Belvedere. The advancement status is that this is only a big picture talk of where we're going. Our current status is we have a demo on Ethereum where we only handle the happy case for now, but we write the demo in good style, that is, the code does not have to be rewritten from scratch later. We are currently only 2 full-time employees, but we're hiring, and our code is not released yet, but you can see it. It will be free software when it's released. Why blockchain matters? Everyone here came to this talk, so of course blockchain matters. A few people say, Bitcoin is just for drugs, scamming, and mindless hodling. But the internet is only for porn, spamming, and mindless trolling, and yet that's what brings us here together today. So it also has useful uses, like people who are avoiding starvation in Venezuela and anything else. And of course, you personally live in the best of governments possible, who would never invest the money to fund world wars. But for everyone else, there is cryptocurrency. And with better technology, we can improve the lives of billions of people, and maybe we can filter out so that there are fewer scams on Bitcoin. And even if they don't win the world, the cryptocurrency are putting pressure on governments toward better fiat currencies. So, problem with blockchain, scaling, that is, the throughput is very limited, and the latency is very limited, like latency in order of an hour. So, that is not suitable for casual payments. You can't go buy a coffee with cryptocurrency today. And there are just not enough transactions. Like and Ethereum, it's 15 transactions per second. That's 9 million per week. That's 400 million per year. That's not enough for everyone. So somehow, some fundamental change is needed to allow scaling. And there's a good reason for the current limits. It's because every node has to check everything. And under this assumption, you can only scale so much. Second problem with blockchain, security. It's insanely hard to write a smart contract correctly. One of the founder of Ethereum had a 400-line contract that lost $280 million to one little bug. So if the co-founder of Ethereum did that, what chance do mortals have to write more complex contracts that don't have bugs? Even posting a transaction in an automated way is insanely complex. If you want to write a program that guarantees, yes, this transaction will be posted like in 2 hours, I challenge you to write a program that I can't break. Like it's so easy to break this thing. To make promises on the blockchain is insanely hard. So amateurs can do it. Even professionals will have a hard time to do it. And one problem is that the opposition is just not accidental mistakes. Your opposition is deliberate attacks by people who want to steal your money or see you lose your money even if they don't get any, or maybe hold your money hostage. Hey, I know how to break your money, now you give me a share, or I destroy everything. So we need better languages to build applications that are secure, and we need robust runtime and libraries to provide valid services. Privacy. Some people want to maintain as much privacy as they can in the blockchain. It's also something that is very hard. I will skip on that. The usual solutions in the fiat world is just have a central processor, say a payment card processor like Visa or other people like that. And it's fast because it's centralized, but the problem is it's custodial. They hold your money, they can confiscate your money, the government can tell them to confiscate your money. So yes, but no, it doesn't apply to cryptocurrency, or not well. So why can't we have that? Because as Nick Szabo says, a trusted third party is a security hole. Sooner or later they will get hacked, or they will get a subpoena from a bad government or something, they will do the wrong thing. So can we have like technical centralization to go fast when we need it, and yet economic decentralization such that eventually if the actor is bad, you can still get your money out thanks to economic decentralization? And I believe this is possible. So our approach is to go back to principle and ask what is a blockchain, find its essential logic, and offer tools that map to the logic of the blockchain. What is the essence of the logic of the blockchain? So we take the smart contract analogy seriously. What is a smart contract? Most people on Ethereum say, oh, a smart contract is just a stored procedure that you execute. That's not how we see a smart contract. I will explain you how we see a smart contract. So we see the consensus as a core system to avoid and resolve disputes. And we want to write our distributed applications using logic and extract the computation from the logic. So consensus as core. What is a distributed consensus for? Basically, it's a system to prevent and resolve disputes. I will skip this more economic slide because it's a more technical audience, and let's finish this. So you don't go to court for casual payment, you go to court only when there's a dispute. The same thing, we can have a system where most of the transactions go fast on a side chain, and you only need to go to the consensus when there's a dispute or to prevent a dispute. There's an analogy between a consensus and a court, but of course the analogy breaks down. In one case you have humans resolving disputes using rhetoric, using social enforcement, etc. And the outcome of a judgment is uncertain, because you never know whether the judge will say yes or no. In another case, we have smart law, where smart is a term of art. That doesn't mean that people are smart, it means that you have dumb computers that follow an algorithm. So smart means algorithmic, it doesn't mean smart people, it means dumb computer. It is a term of art. And in smart law you have machines that use algorithmic enforcement and use a consensus, and the interpretation of the contract is very rigid, and the outcome is certain within the parameters of the system. So, some of you are here are functional programmer. Who is here is not a functional programmer? Okay, so you know that an analogy is one abstraction applied twice. So we need to find the essence of the abstraction and be wary that we use different parameters. The common abstraction is a system for adjudication and the different parameters of human versus machine. So a smart law is not a substitute to human law, it's something different. What law cannot do, why don't we just make the bad things illegal? That's not how law works. Law does not decree bad behavior away, it just makes it de-incentivize. You cannot prevent murder by saying, oh, murder is illegal. What you can do is punish the criminals and de-incentivize murder. And the way it works is by having people have skin in the game. And in human law, everyone has their literal skin in the game. Like, if you do something really bad, we'll catch you and find you. On the blockchain, there is no such thing. Everything is somewhat anonymous. So the way it works is to have a smart law, you need to deposit a collateral on this contract. And that's the thing that will hold you accountable. Oh, if you behave badly, you lose this collateral, you lose your bond. So there's a branch of economics called economic analysis of law. I'll skip that. The main thing is that it's all about the alignment of interest between people. There are ways to align the interest between people, and eventually the only way that allows interest to be aligned is what we call enter or free competition. The fact that if you're dissatisfied with who you're dealing with, you can find someone else, and there is no monopoly. And that's what, in the end, creates alignment of interest. So, for payment processor, if you want to have a credit card or something processor, the way that you will hold them accountable is if you can not just say, hey, I'm dissatisfied with my service, not just say, hey, I want out of your service, but hey, none of the code processors satisfy me, so I can build a new one. So that's what brings the freedom and competition and make the system work. So we want a system where you can pay on a sidechain, and you can easily go from one sidechain to the other and not be locked. And there's an escape clause so that you cannot be locked in the sidechain. So the consensus as court, I skipped most of these slides, but I believe it's a fruitful point of view, where the consensus provides the arbitration and not the transactions. And the transaction can go fast in a sidechain, and you only go to the consensus to resolve disputes. So what are these smart contracts? So we can solve scaling issues by just not publishing transactions on the main chain. So the thing that's very slow is this main chain, where the consensus can have something like 15 transactions per second. Well, we don't solve that, but what we do is we don't publish transactions. If we don't publish them, it can go much faster. We're only limited by the speed at which we can publish them on the internet, the speed of the internet rather than the speed of the consensus. So non-publication is infinitely faster than publication. You only publish the Merkle tree of all your transactions, and everything else doesn't need to go on the consensus. You also need to publish the lawsuits. When there are disputes, you need to publish what happened, the smart lawsuits. But if you design your system well, you have few and far between lawsuits because the incentives are aligned. So people don't want to do lawsuits and lose their money frivolously. And non-publication is good for contracts. You can also have a contract where you don't publish the text of the contract. You write your contract and then you only publish a salted hash of the contract. So the way that works is that just like in human law, where a contract is something that you don't intend to go to court with, in a smart contract is something you don't want to resolve with a consensus. So a human contract is something where you say, oh, I provide this service and in exchange you provide me this money, or the other way around, or some combination of the two. And before you write the contract, you're not going to give the money for free or give the service for free because the other person is not obliged to give you anything in exchange. But after you write the contract, now you know that you can trust the person to provide the service, and if they don't, they're going to be in trouble. So contract is a way to align your interest, to make your interest align. And it's the same thing for smart contracts, where you can write a smart contract to create obligations and align your interest so that now you are going to cooperate because you know that you have more to lose at not cooperating than at cooperating. Whereas before the contract, you have more to lose at cooperating than not cooperating. So it aligns your interest. And the way you keep your clauses private, you don't need to reveal the clause until there's a dispute. You just register the hash of the text of the contract, and you have the only thing that's public is the fact that, oh, I put this earnest money, you put this earnest money, and we agree that if we both agree at the end, we can get it back in whatever proportions we want. So the way it works is that you put your earnest money, you do your thing outside of the contract, and at the end you settle. So the idea of the contract is that most of the work is not done in the contract. Most of the work is done outside the contract. The contract is just a tool to align your interests. So it's a very different view of the issue of, oh, smart contract is computing on the blockchain. No. Computing on the blockchain is literally millions of times more expensive than computing on Amazon, which is itself quite expensive. And a smart contract is threatening the other idiot to go to the blockchain and have him pay for computing on the blockchain if he's stupid enough to not do his part. So you don't compute on the blockchain, you threaten the other person with having them pay for computation on the blockchain and still lose their money at the end if they do it wrong. So it can be smaller, cheaper, faster, and private. So what are contracts for? To create alignment of interest. The plan A is never to go to court, and it's not to evaluate code on the blockchain, it's to do all the work in sidechains or state channels or whatever, but anything on the blockchain. So what does the contract consist in? It's mutual obligations. I promise that I will do this, I will do this service, or else I lose this bond. You promise that you do that, or else you lose that bond. So it's a series of clauses. Each clause has a participant making a promise and has a sanction attached to it. So a threshold contract is an atomic swap. Let's say we are both want to exchange, say I have too many bitcoins, I think that Zcash will go up, I want to buy Zcash. You have too much Zcash, you want to buy a Bitcoin. So we want to exchange, but before we have a contract, no one wants to do the first move because then the rational thing for the other person is to not do their move. You write a contract that says, oh, I will give you the money or else I lose even more money. I put $4,000 of good money, earnest money in this contract so that I will lose it if I don't do my part. So now you trust me, you send me the money, I send you back the money, and then we settle and everyone is happy. So the settlement is slow, the settlement still takes like an hour or whatever, But as soon as a contract is signed and the contract is registered on the blockchain, it's as good as confirmed. You know that you will be good. There is still a new kind of attack where I can have you sign the contract with me and deposit your earnest money, and then I DDoS your machine, so you can't do your part, and now I claim your money as reparations. So if you sign a contract like that, you want to have a solid system with redundant machines on several different internet connections and data centers to help you. Otherwise, I advise against using these systems. So second good news, we solved interoperability. So as we saw, we can write a contract between two completely different blockchains, and as long as we can express in logic what's going to happen, we can write a contract and then interoperate between two blockchains, even if the two blockchains have no means to write contracts in either of them. So we can do currency swaps, we can do any kind of operation between several blockchains, and there is always this free option problem. The free option is when you write any kind of contract, since it's asynchronous messages, the last person to send a message has the option of either timing out or sending the message. So he has a free option. So he can look at the rate, how the rate moves. Oh, after all, yes, I'm going to take this contract. Oh, no, the rate moves the other way, so I'm not going to take this contract. So there's a free option problem. You can kind of work around the free option problem using a facilitator, someone who matches you and has no interest in the deal. So there are always solutions, or not worse than previous systems. If you want to swap without a large stake, you can, instead of depositing $4 million or do a $1 million swap, you can deposit just $4,000 and do $1,000 swaps. So you can, and if you have state channels, as in the Lightning Network and Bitcoin, you can do that fast. So yes, in this case, you exchange the fact that you only need a smaller amount of bond, but then you have failure scenarios where the exchange is partially complete. Instead of being 0 or 1, it can be partially done. Okay, so what does that tell us of the logic of smart contracts? Law is about verifying compliance and punishing non-compliance. And once again, smart is a term of art for algorithmic. And smart law is compliance with algorithmically verifiable rules. So we need to have some kind of logic to express the thing that happens. And this logic will, let's look at what this logic looks like. So what is a legal argument? It's when two parties disagree about a claim. I claim that I did send you this Zcash, you claim that I didn't. So we go to the contract. How do we convince the contract who did or didn't do his part? Well, each party will argue its case and show his witness. And at the end, the judge adjudicates the case, he finds who's right and says, this person was that person. That's called an interactive proof. And there's a part of logic called, mathematical logic called game semantics that deals with it. So what is an interactive proof? Let's argue that all sheep are the same color as mine in Massachusetts. How can I do that? If I argue with the judge, as a formula, there exists a sheep that's mine, and for all other sheep, there is properties that sheep are the same color. The thing I would typically try to prove is all my transactions are valid. And here, so all sheep are white. So one way, a brute force, is I show 500,000 sheep to the judge. So that's a brute force approach, and that's maybe the validator. That's the way Bitcoin works, to show all the transactions to Bitcoin and the validator determine that they are correct. Unhappily, that doesn't scale, because if you need to, well, it only scales so much. So if you want to show actually this million chips to the judge, he will fall asleep, and then he will retire and die of old age, and you still won't have your adjudication. What you can do instead is say, hey, I'm not alone trying to prove that to the judge. I have someone who is arguing the opposite. Like, I'm arguing that I paid my Zcash, but you're arguing the opposite. So we can do a game with the two of us and accelerate. So I'm going to try to argue that there exists an x, such as for all y, p of xy, and you're going to argue that for all x, there exists a y, such as not p of xy. So So I'm going to show my witness for that there exists. And then you are going to show, then I have for all would be very expensive for me to show a petabyte of data to the judge, but it's cheap for you to show your witness. So I'm showing my witness x0, exhibit your witness x1, y1, and then each witness removes the quantifier. At the end we have a closed formula. The judge can just plug the witnesses in the closed formula and decide, adjudicate the case and who is right or wrong. And game semantics can translate any formula into a verification game. And if the formula is provable, then there is a winning strategy for the guy who can prove it. And if the formula is decidable, if the formula is decidable, then whoever in the future will be right will have a winning strategy. So when you write a contract, you don't know in advance who will or won't do his part. So you write a decidable formula so that whoever does or doesn't do his part, whoever does his part will win and whoever doesn't do his part will lose. And if all the quantifiers are over known finite data structure, then the good guy wins because the good guy has a winning strategy. So what is the logic built on game semantics? There is something called computability logic, where, so many people have done game semantics, oh here's logic, let's find the game semantics that corresponds to it. There is this guy, Japaridze, who did the opposite. He thought, hey, here are these games, what are the logic that correspond to these games? And I think this is a more productive approach to building a logic in this case. So the game semantics first, semantics second, and you have fragments this way of classical logic, intuitionistic logic, and linear logic that appear naturally from game semantics. You can also define your own logic operators, and we will have to do that for the blockchain. I will tell you a few of them. And for the blockchain, you also want like modal temporal logic, epistemic logic, and other fragments like that that correspond to the blockchain. So I suppose this is the most important slide. This is a slide where I have a high-level view of contract. Most people see a contract, oh, this is a low-level virtual machine that executes code on the blockchain, stored procedure. But my view of how you program a blockchain is like 4 levels of abstraction above that. What you want is write a distributed application where we do something that involves money, but the interesting thing is what the user level approach and what our messages exchange between players. So that's the level of abstraction that I care about. And the contract is just a piece of agreement that holds our interests aligned so that we're interested in doing the thing and not cheating, because whoever cheats loses. So the contract is this piece of logical specification. And a lawsuit is an interactive proof, which is only a small piece of the contract. And the contract invocation, when you go to the blockchain and invoke the contract, is only actually a small piece of the lawsuit, which is just an interaction step in this interactive proof. And the contract GM is a thing that executes this interaction step. So it's 4 levels of abstraction down from what is interesting. The thing that is interesting is a distributed application, is the interaction between the players, the interaction between whoever does something interesting. So that's why all the existing languages to develop smart contracts are desperately low level. Like there are 4 levels of abstraction down what is interesting. So it's like writing an assembly language instead of DSL in Prolog or something. So I want you to program using logic. Once again, the programming language is low level when its programs require attention to the irrelevant. So now we have 4 layers of irrelevant that you don't want to care about, so you want something much higher level. Your contract invocation, even with a functional programming language like developed by Tezos or by Cardano, is still way too low level. You want to program in the logic invariance of your distributed application, and you want to use a distributed a domain-specific language based on the appropriate logic to develop it. You still need a low-level VM for the contract, of course, and the way it does is that you want to translate automatically the logic into a program, and that's the essence of functional programming or category theory. You take a logic and you extract the program using whatever isomorphism of the day, transform one to the other. There is an issue, the number of interaction steps. If there are, let's say, if we allow for 2 hours for each challenge period for an interaction step, if you have 100 hours, if you have 100 quantifiers in your formula, that's 100 times 2 hours, that's a lot of time, like many days. Probably you want to minimize the number of interaction steps, and you can do that with a technique called scalability. If any of you has learned logic, it's a technique to remove quantifiers from a formula, and it works like this. You have a formula of the form, for all x, there exists a y such as p of xy, so that's for any challenge x, I can reply a challenge y, I have a response y, and the formula is satisfied. I transform that into, hey, I'm going to give you a lookup table of all my possible responses. So later you're going to give me a challenge x, but already I'm going to give you an f that is a lookup table that, or a formula that explains how I'm going to respond to your challenge. So I'm exchanging, I'm swapping a there exists and a for all, and therefore I can put all my for all on one side, all my exists in one side, and I can have only one exists and one for all, and a formula with 2 steps. So any formula can be reduced in 2 steps, but of course it's a trade-off between space and time, because you need to build all these huge lookup tables or formulas to compute. So it's a trade-off between space and time. But if we get, if we do it right, it will be paid by the bad guy, because the bad guy is guaranteed to lose in these things. There is a need for third-party litigation. So what happens is there's a litigation. Let's say I manage some money for all of you. And someone comes to me and tells me, I want the pot of gold, give me $1 million. And I tell them, go away. The normal reaction, I don't owe you anything, go away. And you pay the court fees. What if instead of telling them, go away, I say, oh yes, here's your $1 million and all the money. And all you, hey, this guy is eloping with our $1 million and the accuser is probably a civil identity, an accomplice, and they're just taking the money away from us. So what you want is the ability for any of you, or anyone who represents you, to go to the consensus and argue, this guy has an invalid claim, and that guy is not doing his job properly at rejecting the claim. Therefore, you should reject that claim. This guy loses any right to be a manager because he's a cheat, and we'll find a new manager or a new set of managers. But the good guys keep their money, and the bad guys don't get the pot of gold and pay the court fees. So we need third-party litigation. That's something that does not usually exist in human law, but that is necessary with smart contracts and well, this interactive proof. So why do we need formal methods? Because if you have this point of view of this high-level point of view, obviously the solutions appear like, oh yes, I need game semantics, therefore I need this kind of games, and oh, I need third-party litigation. It appears naturally. If you don't have the correct point of view, you will never understand what to do, and you will just fail. Also, there are many moving parts, so I need formal methods because I want to make sure that all these moving parts are in sync with each other, because if there's any discrepancy, it's a bug, and someone will lose money, or the bad guys can win. Most parts can be fixed after deployment, but the contract cannot be fixed. So maybe you can fix a bug in your server or your client or something after the deployment, but the contract after the deployment, it's done. So if there's a bug in it, the good guys lose. You don't want that. You want to use formal method to make sure the contract is correct. Once again, if the greatest specialist lost that much money with 400 lines of code, we can't do that formal method like mere mortals like me cannot do. So here are some kind of moving parts that need to be logical consistent. A logical specification explaining to your users what your program is doing. Because why would they even consider using your dApp unless they can agree on what they want and the fact that what your dApp does is indeed what they want. So you want a logical specification or something that explains to the users, hey yes, here's a good idea to use this application, it does what you think it does. You want to extract the actual code for the clients, for the servers, for the verifiers. You want to extract the on-chain contract, this stored procedure that holds the actors accountable by playing this game of referee. You want to extract the on-chain lawyer strategies, the people who present those witnesses to the judge. You want to extract the code that does that. It's not enough to have, oh, there is this winning strategy. Well, you need to play the actual strategy to get your money back. So you need to extract that code too. You also need to extract maybe off-chain lawyer strategies to advise people. Yes, you should do that, or no, you shouldn't do that. Oh, if you do that, you are going to lose money because you have a contract that says this. Or maybe, you're going to lose money in the contract, but something, the rates have changed so much that maybe you should just drop this contract and accept that it's foregone. There are many things that the lawyers can advise you without executing code on the blockchain. And of course, we want to extract tests that prove that the bad guys try to do something bad and fail. Because if you just prove it correct and never test it, that your program is probably buggy. So you want to extract the test and run the test in the test net. And if there's any discrepancy between any of two of these parts, the bad guys can probably win and the good guys can probably lose. So the solution is to extract all these moving parts with, say, specification, and then you want a programming language that has three aspects: present, past, and future. The present aspect is a part that creates a distributed multi-party computation out of a program that's some variant of the calculus or whatever multi-party distributed computation language you have. The past thing is where you generate a verifiable trace of execution that can then be checked by the consensus on the blockchain, by the contract with the judge. And you want to have a future aspect where you want to be able to reason about all the possible future traces of execution and prove that if I do my part in all possible futures, I won't lose my money. If you do your part in all possible futures, you won't lose your money. So you want to be able to prove invariance such that none of the player will lose his stake if he does the right thing, regardless of whether all the other people do the right thing or not. If I do the right thing, I won't lose my money. And the other people I don't control, but I can control myself. So you can use, there are three different ways that you can assert or validate invariance. You have economic validation, interactive proof, or non-interactive proof. Economic validation is the thing that on which all the blockchains are done. It creates a consensus, but it can be captured by 34%. If you capture 34% of the network, you capture the whole thing. It's very capital intensive, everyone pays. But as far as checking an invariant, it's very fast. You can check the invariant in milliseconds. You can have invariants that have both existential and universal quantifiers. All the invariants must be public because everyone knows the invariants that are going to be checked. And the complexity is done already, so relatively easy. An interactive proof is the thing I propose. It requires that a consensus already exists, but as long as there's one validator on the network, the proof can be proven. He can play the winning strategy. The cost is really cheap. It's very cheap. Since you only do the computation when the bad guy does something bad and the bad guy needs to advance the money and loses his money, it's very cheap for the good guys. The interactive proof. The bad guys pays. The latency, on the other hand, is bad. It's a matter of hours for one challenge step, and then if you have two challenge steps, it's 4 hours, and etc. etc. Quantifiers, you can do all kinds of quantifiers. Privacy, you can keep your contract private, and the complexity, you have lots of moving parts, so you really want to generate that automatically. There's also something called non-interactive proof. I don't know if you've heard of ZK snarks. It has different trade-offs, and one of the trade-offs is that it can only do existential quantifiers, which sometimes is enough. It's also expensive. It's also a case where the good guy pays for the non-interactive proof, whereas in interactive proof, the bad guy pays. So there is another problem. How much time do I have left? Can I do that or not?
20 minutes.
10 minutes?
20.
Oh, 20. Okay, good. So let's talk about the need for shared knowledge. What if you want to prove that all sheep, or that there is a black sheep, but the black sheep is hidden in a hangar? What if you prove that there is an invalid transaction, but the invalid transaction was never published? So you know it exists. Someone asked for $1 million, and you know that you didn't give him the $1 million, but as a manager, I just published a Merkle root of the tree of the transactions, and in the middle of this transaction there is some invalid transaction, but I don't show it to you. And therefore you can't show to the judge, here is the invalid transaction. So the bad guy wins. So the winning strategy requires you to be right, and it also requires you to know how you are right and how the other guy is bad. So for the good guy to win, you need shared knowledge. And if you have a closed contract with a finite number of people who read you all the data all the time, then the shared knowledge is easy, but there's no scaling. You have things called state channels or payment channels. Everyone signs every contract, every transaction. You know what's in or isn't in the system, so there is no cheating. So you can use interactive proof readily in this case. With an open contract, it's easy to scale. So you can add millions of people with one manager. That's very easy to scale. The manager can do things in sequence. So with 1 million people, you can't have everyone sign every message. That's not doable. But you can have one person sign everything, and that's easy. But then how do you build a shared knowledge? How do those millions of people check that there is nothing funky happening, since they are not signing the message and not seeing the message? And that's why we need what we call a quote registry. A quote registry is an oracle for public data availability. It makes sure that the data is available. So now you can say, hey manager, you can manage the sidechain however you want, but you must publish each and every transaction and have them signed by this quote registry that says, yes, we have seen this thing and here it is, and anyone can see it and check that it is valid. And if there is a quote registry, then you can build shared knowledge over arbitrary sidechains and data, and you can scale them. So the quote registry allows for third-party verification of all transactions, or in some case you can move some of the relation into the quote registry. And it's a solution to the block withholding attack, the attack where the manager does not publish his data. And notice that it's not enough to have a pre-image of a hash. You need the pre-image of the hash and all the transitive data in the thing. So it's not enough to have a pre-image of the root of your Merkle tree. You must have a pre-image of transitive pre-image of the entire Merkle tree, because the invalid transaction does not have to be at the root; it can be anywhere in the Merkle tree. So if you have this quote registry, you solve the data availability problem. That's a big if, though. And in practice, to solve the quote registry, you need a economic validation of the system. So you don't get a free lunch, but that's the same issue as that everyone else has. So if you believe in blockchain at all, you believe that economic validation is possible, and so therefore building quote registry is possible. So there is a 50% attack, as in anything. There is also a 34% attack. Not go into it. There's always this oracle dilemma. If you have a closed registry with a finite number of people who are well identified, and you know how to go to human court after them if they are dishonest, okay, but then you're back to the that works, but you're back to the social enforcement problem in the end. And if you have an open registry for this quote registry, then anyone can buy shares of the quote registry, and if you buy enough shares of the quote registry, you can start lying and capturing the quote registry. Well, then bribing is legal, and that's different points in. So there is no perfect solution, but once again, if you believe in blockchain at all, you believe that this is solvable, that you can have a system that is capitalized enough that it capitalized enough to protect the money that is into it. So don't put $1 billion into a system that is only protected by $1 million worth of quote registry. You must only put money into a system that is protected by more than the system. Shared knowledge and common knowledge. So in epistemic logic, there's this notion that shared knowledge is what everyone knows. Let's say that everyone here knows the programming language Prolog. Well, maybe you do, but that's something rare, so you don't know that the others do. So it's shared knowledge, but it's not common knowledge. Common knowledge is what everyone knows that everyone knows that everyone knows that everyone knows. So if I say, hey, does everyone here know Prolog? And, well, no, okay. Does everyone here not know Prolog? And no one responds yes, then suddenly you all know that everyone knows Prolog, and it's common knowledge that Prolog is known, and then we can start writing Prolog and no problem. So shared knowledge only requires one round trip. I teach you Prolog in parallel, or I send you the instructions, and after one round trip, I know everyone knows Prolog. Common knowledge needs everyone to talk to everyone to talk to everyone, and therefore it's slower. And so shared knowledge can be done with one round trip around the world by just broadcasting the data and getting the axe. And common knowledge requires much more time. And common knowledge is what the consensus builds. and therefore that's why the consensus is always more expensive to build than this shared knowledge that we depend on. So our solution can help scale because we only depend on shared knowledge for normal transactions. And it's cheaper. So we can do reputable facilitators where you have a contract where there's a manager, and if at any point the manager fails, you can force the manager to do the right thing by publishing on the main chain or another facilitator, hey, I really want this to happen, they refuse to sign it, make it happen. And you can, so they cannot keep your money locked, they cannot raise their fees arbitrarily high, because if they do, you just go to another facilitator and then he handles your transactions. So it's a system, you can have a system where most transactions are fast because most of the time most of the time you're using a facilitator you can afford and who doesn't censor your transactions. And if for whatever reason it becomes too expensive or they start censoring you, you can move your money out without their consent. And that's slow because it will take a few hours to happen, but they cannot prevent it. So at the very worst case, you lose your time, but you don't lose your money. You don't lose your principal. They do fast payment, and beyond fast payment you can have facilitator to do exchanges, arbitrary contracts, and etc. And the conclusion is that we can make blockchains, distributed applications secure, scalable, and private by having a suitably high-level programming model where a blockchain is a verifiable trace of computation, and the consensus says this is the trace of computation, so we are going to reason on it and not another candidate that is not the real truth. You can have the one true trace of computation. You can use game semantics to prove arbitrary invariance on your past behavior, and then you can use regular programming language that has these three aspects, past, present, and future, to have the present computation, the verification of the past for the contract, and the reasoning about the future to be confident that the contract is the one you want to enter in. So we at LegiLogic are building this blockchain layer 2 operating system, and we are hiring, and we're also looking for academic collaborators for our R&D project consortium Belvedere. Thank you. And the meta story is that given a problem, we seek its essence, we strip from the incidentals, we try to reason logically about the things with a logic that works for machines and humans, and try to match the computation to the logic, and once again, that's the essence of functional programming and category theory. Here is contact, and thank you, and questions? Yes?
If you have a paper contract, you can cancel the contract by
Yes.
the person tearing up. You have my signature, I have yours, we can tear it
Yes.
up. How do you cancel a contract? If you decide?
You can't unless you have a clause in the contract that says you can cancel it. But in this case, if you cancel the contract unilaterally, basically you lose your bond. If you stop playing the game, you lose your bond.
What if both people decide, okay, we want to cancel the contract?
So a regular contract in my approach always has a settlement clause, where everyone who agrees, well, for a closed contract with a finite number of participants known in advance, then you always have a settlement clause that says if everyone agrees, the money goes out as per the agreement. If it's an open contract with millions of people who use a manager, then that doesn't work. Then you need, it's more complex. Yes, you can, there are ways to get your money out, but it's not that simple.
Do you write the reverse contract and execute both?
I wonder if
In some cases, that's what people do for trading. That they have future contracts and they do two contracts. But yes, this is a logical infrastructure that helps you write those contracts, and then it's up to the traders or whoever to write contracts on top of that. And if your contract has to deal with things outside the blockchain, you need an oracle, and an oracle is something that writes a verifiable trace for things that are not a priori verifiable, and then the question is the oracle honest or not? That's not our problem. Other people are solving this kind of problem for oracles. But assuming there is an oracle, then you will be able to use this oracle in the contract and do arbitrary things with it. Yes?
Yeah, I don't understand your notion of interactive proof.
An interactive proof is where, once again, let's say that Jim and you argue on whether there is a black sheep in Massachusetts. And you argue that there is no black sheep there, all sheep are white. So you want to convince me, the judge, that all sheep are white. So you show a white sheep. And you could show each and every sheep in Massachusetts, but that would be too slow. So instead you challenge Jim. Hey Jim, you're claiming that one of the sheep is black. Show the black sheep. And now Jim has two options. He can show a sheep, and then I'll check whether it's black or not. Or he can fail to show a sheep, and then he times out and he's considered to default and have lost.
So that's completely unfair for him then?
Why?
Because for me it's quite easy, I don't have to do anything, but he has to work really, really hard in order to actually...
No, so the idea is that if we have this shared knowledge network that publishes everything, then it will be, you can just look at each and every transaction all the time. So you need someone who does the hard work.
So it's only an interactive proof over facts on the blockchain.
So what's interesting, so the lawyer has to do work, but work done off-chain is much cheaper than work done on-chain. That's the theory. Like, to do all the work on-chain, you must show 1 million sheep on-chain. You want to exhibit all those sheep on-chain. That's very expensive on-chain. And on-chain computations are literally 1 million times more expensive than off-chain computation. With an interactive proof, yes, he has to find the black sheep, but he can find the black sheep off-chain.
But so what you're saying is he needs to find an example from the blockchain, not from the whole universe as we know it.
Well, yes, from whatever your contracts is about.
Right.
So if you have a contract about this manager doing all his transactions validly, then need to have validators. You need to have at least one honest validator who will look at all the transactions done by this sidechain manager and check that each and every one is valid. So yes, you need a
it's just a way
validator.
of moving stuff off the blockchain, basically.
Yes, so it's a way of moving the validation of the consensus, because the consensus is very expensive. So you can, so yes, someone still has to do the work, but work done off-chain is cheaper than work done on-chain. millions of times cheaper.
Sure.
Yes.
You mentioned linear logic. How do you use that?
Linear logic can be used to model resources such as tokens that you don't want to appear out of nowhere. And so if you can write your contracts in terms of resources that don't appear out of nowhere or that cannot be duplicated, then it's a useful thing to have in your contract. But
So it's up to the contract writer.
the contract writer, yes. Sometimes the contract writer wants to write his logic in the appropriate logic that makes sense for the problem. And then you want this logic to be translated correctly all the way down with a full abstraction, so that you don't want to have a new secret side channels that allow the bad guys to do the wrong thing, bad things. So you want to write your contract in the logic that matters to you and have it translated all the way down to the code that works correctly.
So it does seem like still a kind of issue there, because you know the dApp bug, for example, was a very subtle programming mistake.
Yes.
And what you're talking about here is really quite a high level, what's the right word, strategy
Yes.
for how you're going to conduct contracts, and not an approach for how you're going to check that your code that's running on the Ethereum blockchain is actually doing what you want it to do.
Yes and
There's a
no.
kind of
So
gap there.
you need to check two things. You need to check your high-level contract, and you need to check your toolchain that translated to the bottom. And yes, if you have a bug in your toolchain, you'll have bad surprises. So you need to prove the correctness of your toolchain in addition to the correctness of the high-level contract. And yes, if your model of the toolchain has gaps, then the bad guys might use those gaps to do bad things. So, but there's a finite number of things to deal with. So eventually, you can do it. It is a big endeavor. It's not a small endeavor, but it's a finite endeavor that is possible. And
Not a small endeavor, I think it's an understatement. It's a
Yes,
gigantic
I know.
endeavor.
well, it depends. You can start small and do. You can do it incrementally. I have a Medium post on what formal method can or cannot do. And yes, it is an endeavor, but how much money are you going to put in a contract that has not been proven correct? Can you afford not to prove it correct?
So I do agree with that.
Yeah, so that's why it's not for everyone. It's not cheap. Formal methods are not cheap. it will cost millions of dollars to build this piece of software. But if you're going to put $280 billion in the contract, maybe you should afford a few $1 million to make sure it's correct. And that's why formal methods are not for writing your like a Pac-Man game, no. But for writing smart contracts where millions of dollars or billions of dollars are at stake, I believe that's.
And do you think people are prepared to pay that money?
I believe people, at least some people, are ready to pay. I only need to find one set of people ready to pay it once. And I found some people willing to advance some money into it already. So it's up to me to build more things, to find the right partner to build it with me, and to convince them to put more money in it. Because, yes, it's worth it. I believe that this $280 million failure was probably preventable, and the next one will be preventable. Maybe that one was not preventable, but the next one will be. So do not put $1 billion into smart contracts unless you've done the right work. Oops, and this contact info has changed, but that's okay. Here.
What's
Yes.
the current state? Like you mentioned this tool chain that you want to verify. Have you
Yes.
started building it?
So, where do I have? What do I have somewhere? Yes, right now my current state is I have a demo on the server. I have code written in Objective Camel that purports to do the right thing, and that hopefully we can translate to Coq at some point. It also tries to address problems like posting a transaction in a safe way, or having an API such that maybe my current transaction poster is not perfect, but it will get correct, and you can actually prove it correct at some point and have it be abstract from the rest of the code. And so I'm organizing my code in a way that, yes, this is an architecture that makes sense, and you can check that it makes sense. You can look at the code. Right now you have to send me your GitLab address to look at the code, but yes, you can look at the code. And we also have a demo contract. We don't handle all the bad cases, but we show here's what it looks like. Here's what the code that we want to generate will look like. And we have this system of claims and challenges where you register a claim. And here are a few ways that this claim can be this claim rejected. And if no one rejects the claim during the challenge period, then the claim becomes valid. And then, based on the valid claim, you can take money out, for instance. So I claim that I have a $1,000 in an exit ticket on the sidechain that has not been claimed before. And so I make this claim, I post this claim on the blockchain, on the contract. And if no one disputes the claim, then after, say, 2 hours, after 2 hours have elapsed, no one has disputed the claim, so I'm executing the claim and taking the $7 out. So that's the kind of thing we have. And yes, it's not sufficient. It's not a full product. That's why we're hiring right now. And maybe if you're interested in working on these things, we're hiring.